Hey, good afternoon. Okay, before we get started, you're roughly halfway through your first sprint. So how's that going? How are you finding ways for your team to meet? Are you meeting regularly? What's happening?
Our team's meeting 3 times a week for quick little update meetings, and then whenever we do work on stuff, we just get on Discord.
Okay. And you had a sprint planning meeting. True?
Kind of. It was a little weird because the assignment with the sprint planning in it was due on Wednesday, and the sprint started on Monday.
Yeah,
So we
so
started a
technically,
little-
yeah, there's a fuzzy boundary there, right? So technically you would have the sprint, pre-sprint stuff done, which is just the backlog, and then the sprint planning meeting would be deciding what to do in the sprint. So the pre-sprint stuff was really more project related, and then this sprint was supposed to be more sprint related, but I recognize there's a very fuzzy boundary there. How about other teams? I'm pretty sure there's more than one team.
Hello, I just joined. What was the question?
How's your first sprint going? Is your team able to meet regularly? How often do you meet? How often are you doing scrum meetings? Did you have a pre-sprint meeting? How did this all work out?
I believe for my team, it's going relatively good. We've had a few meetings. Everybody seems to be in good communication. We have project idea down and have already started on it.
Do you have a regular meeting schedule?
Not entirely. Yes, but not 100%.
So like the deal with the scrums is you want everybody to know, okay, we're going to meet up on 10 a.m. Monday, Wednesday, Friday. That's a goal. If you make it ad hoc, it gets harder to maintain discipline as the semester goes on.
Okay.
Anybody else? Okay, and everyone's sending me Discord, and I'm still catching up with that. Discord links to their servers, and I joined, Brandon, I joined your team's server just like an hour ago, but it won't show up on my list of servers that I belong to. So I don't know what's going on. Me and Discord never get along.
Maybe try rejoining, because looking at it right now, I don't see you.
Okay.
Also, I know you did send an email.
What I need to do, I'm gonna play around. I was logged in already, and then I did your link, and it asked me to log in again, which I don't understand. And then I logged out entirely. I'm gonna log back in and see if it joins up, syncs up then. Otherwise, I'll just log out and do just your link and see how that goes.
Okay.
So I'll play around, but the help features were not helpful. Yeah. Okay. Okay. So yeah, we're here. You're in the middle of your first sprint, roughly speaking. As you know, I'll be a little bit flexible with due dates because everything's due on a Sunday according to this, which doesn't really work out that great, or a Monday, and you may not have time to. You may need your Monday to pull stuff together and turn it in Tuesday, that kind of thing. There's a homework posted that I don't think will take that much time. They're not designed to take a lot of time. Hold on, we got some. Yeah, okay. There's a never expiring one in the discussion page that I can look at too. Okay, and then, so this week we're talking about design. Next week we're talking about configuration and tools, and some of that has to do with GitHub, and I suspect about half the people in this class already know more about GitHub than I do. That's fine, but we'll talk about how to try to use it in a disciplined way. And the reason that I don't have that much direct knowledge of GitHub is because the way you learn tools like GitHub is to use them, and I very rarely have an opportunity to do real programming. So I just don't have I haven't had the opportunity to build up my experience on that. That's where we're going. This week's lecture is a mixture of review from stuff that if you had me for CS225, you've been exposed to. So it's hopefully a reinforcement of that. And then some additional material that kind of places what we did in CS225 in context of the larger picture. Are there questions or concerns about anything before I go on to the lecture material? Okay. So design, as usual, with the outcomes at the end of the week, be able to explain these outcomes to somebody. Prove it to yourself by explaining these outcomes to somebody. And the way this is set up makes perfect sense from an information presentation format where we start at the high level and go into the, you start abstract and then you go into the details. So it starts with high level, goes to low level, and then talks about the software design document. The way this works in terms of what you need to know for the course, though, is in the reverse order. So I'm actually going to do this in the reverse order. So we'll start with the design document and give you some information about what the expectations are for that. Then we'll talk about low-level software design, which is where most people are in terms of a project of this size. In a project of this size, you rarely think in terms of high-level architecture type design because it's not big enough to warrant a lot of consideration. Real world projects are big enough where you would have to worry more about that. So let's start down at part 3. It's a lot of slides here. I got rid of Dr. Ochoa had a lot more. I got rid of a bunch, right? So all right, so how do we document in this software design document? Okay, that doesn't tell us anything, right? What does the software design document have in it? Okay, it should have a description of the software functionality so that people understand what it is that you're trying to build. And in yours, I'm asking you to put in the textual description and then carve out the functionality in terms of requirements, not requirement specifications, but requirements and user stories. And the goal for that, the reason for that is, number one, the text description makes you provide all the definitions that are needed in order for things to make sense, gives people a natural language flow of what the product is, what it does, what it doesn't do. It gives you a chance to put in the citations as you need them for either trademarked items or formulas or claims about how things are done. You know, if you're doing a statistical model, you really need to have some statistics in there. And where do you get statistics? Oh, you get that from a statistics book. Or maybe you're doing a simulation that's similar to another simulation that somebody else has already done. Oh, okay, you can gain validity for what you're doing by saying, look, we're doing it like these guys over at Caltech did it, or MIT did it, or whatever. They publish their results in a journal or a conference, and then you can utilize what they did as a basis for what you're doing. That's a common thing to do if you ever publish anything, is to show related work. You know, how are you differing from other people's work? How are you the same as other people's work? Okay, requirements, problems that we talked about last week don't always make sense, contradict each other, incomplete, inconsistent, vague, or wrong, et cetera, et cetera, et cetera. We don't need to worry about the analysis too much, but the thing that's important on this page again is then you have a model. And what's a model? and abstraction. Let me talk about this for a minute. I used to work at a place called the Institute for Simulation and Training, and as its name implies, we did a lot of simulations of things. And in order to do a simulation of things, you would create a model of the thing that you were going to simulate. So if you want to do your disease infection rate simulation, you need a model for how diseases go through populations. Now, you will never have a perfect model, because if you had a perfect model, you've actually got the real world thing. So you may have, let's go with the disease infection rate model. You have to decide how you're going to model, say, individual humans that can get infected. What are you modeling about that human? Hair color, eye color, genome, whether they like ice cream or not, right? You take that whole entity that you're modeling and you abstract away and pull out what's interesting to you in terms of the model. So it might be in your model, you just have them as a number. They are human being number 82. You may or may not have associations with how they might move about in the world and how they get infected or don't get infected. Well, even that you can abstract. Are you actually going to have pathways, and these individual humans walk around on pathways? Do they all meander around in a big, basically a big empty plane where they may bump into other people? Or do you just say, this person's outgoing, they have an 80% chance of running into other people in a given time period, and these people are not, so they only have a 20% chance of bumping into other people in a given time period? Or here's the number of people that they tend to associate with over the period of a 24-hour period. That's an abstraction. I mean, you can actually model people going to the grocery store and walking up and down the aisles, but boy, that's a lot of work. And it might be easier just to say, we have 3 classes of people. You know, people who don't meet many other people, people who meet the average number, and people who meet a whole bunch of people all the time. That's a lot easier to model. So you're pulling away these abstractions. And we, in order to emphasize that point, we had someone actually publish a paper. You know, we publish papers all the time about modeling, and you know, something as simple as an elevator. What is in the model and what is in the real world elevator? Well, the real world elevator has a smell. You probably don't model that. It has a taste, which you probably have not experienced and shouldn't model. But the point is, there's so much stuff and you have to pick and choose what you're going to model. That's an abstraction. Now, what are we doing here? How does this relate to the requirements? Oh, okay, you're going to model the design of your software. The full model of your software is the software itself, every single line of code. Well, if you want to talk about the design of your software, that's too much information. You don't need that. Just like you probably don't need to know in the infection model if the person, person A likes strawberry ice cream or not. That's unnecessary information. So what do? You pull out the portions of your code that are relevant to someone who wants to understand how you put it together, what the piece parts are, what jobs the piece parts do, and what information the piece parts keep track of. And I'm saying you pull it out of your software, but as you would expect, you design first, and then you implement second. And then you always have to make sure that your design matches what you actually implemented. So the design may change as a result of implementation. So you're pulling out enough information where someone can look at your software design document and say, okay, based on the textual description, I understand what this thing does and doesn't. Based on the requirements, I can confirm specific pieces of functionality. Based on the user stories, I can confirm specific pieces of functionality. And then that's what we want it to do. And then we talk about, okay, but how did you actually achieve that? What's the actual design? Oh, that's where we go into the UML diagrams, the class diagrams. Oh, I see. You made these classes. This class does this job. This class does this job. This class does this job. And how do they relate to each other? Oh, we have a diagram that shows the relationships between them. So that's the goal here. Does this make sense so far? Do we have questions yet?
It makes sense.
Okay. So again, models allow us to understand by focusing on just the essential details. And in terms of your design depiction in your document, the essential details are the classes that you have, the attributes that they have, the methods that they have. What do those methods do? Not how they do it, that's the implementation, but what do they do? And then the relationships between the classes, which pulls us into unified modeling language, which again, those of you, how many of you guys have had Behe for CS225? He teaches it in the summertime. Does anybody here have Behe, or did you all have me? I'm going to say everyone had me. Okay. So hopefully you remember something of what we talked about in CS225 about unified modeling language. I forced you to make a class diagram in that course, and now we're going to expand on that a little bit. The unified modeling language is larger than just class diagrams. There's 12 plus, depending on who you talk to, different kinds of diagrams. The class diagram is a nice snapshot of the overall design, but there's also data flow diagrams that talk about how the different classes communicate and pass information around. There's use case diagrams that talk about how users will basically poke the system, and then what does the system do in response. There's a bunch of different diagrams. We're only going to worry about the class diagrams. If you take additional software engineering courses, you will be introduced to more of these diagrams. I'm also going to pause to note that depending on what agile community you're in, some will say, we don't need any of these documentation, right? There's some very extreme forms of agile where basically literally the code is the documentation. But in order to make that work, you still have to have some way to abstract away the details of the code in order to not have to always deal with line by lines of code. Those systems tend to use tools that have some kind of annotation in addition to the code itself. So, you know, you may find yourself in a situation where they're saying, oh, we don't use UML diagrams. But most people do. It's as a popular a way to represent object-oriented code as anything else. And as you would expect, people do a lot of studying with this. Okay. Dynamic models and static models. We're focusing on the static model. Remember, dynamic always means behavior. It means things are changing. So dynamic models are showing how things change, like a use case model or a data flow model, where you're showing how the data moves around in the different pieces of the software. How, you know, the user wants this to happen, so they talk to this module, which makes a request of another module, which makes it right. That's a dynamic diagram. But the static one is just describing, look, here's our classes, here's how they relate to each other. What I'm going to add over and above from the CS225 work is more textual description. Basically in 225, I was concerned with, look, give me a picture and talk to it a little bit in your text. But here I'm going to ask for more text to describe what's happening. Okay, UML class models. You're focusing on the individual classes and then their interrelationships. And what you're showing on the classes is the name of the class, the attributes, the methods or operations, and then associations between the classes. Okay, what relationships do we worry about? Basically, the is a relationship, the has a relationship, and the knows about relationship. The is a relationship, that's the inheritance relationship. Parent, child, parent extends child. Child extends parent, I'm sorry. The has a relationship is when one complex object is composed of another one. And there's two subforms of that, which we're not going to really worry about in this class: aggregation and composition. In aggregation, you're composed of, you have, my example here is a student club. The student club could go away, but the students still exist, right? They exist outside of the club. So in aggregation, the individual elements exist independently of the thing that was aggregated. Whereas composition, you need that part to, the subpart to make the larger part. And if the larger part goes away, then the other part goes away. So I'm saying if you have a human, that human, you know, a record of a human, a model of a human, you're going to have certain things that go with it, like a name, first name and last name and social security. Those actually compose the human model, because if you didn't have the model, you would have no need for a social security number floating around with nobody attached to it. As opposed to the student club. You can have a student floating around on campus not attached to any club, but you're never going to have a social security number not attached to a person. So that's a good distinction to know, and we will, I'm basically going to ignore that distinction through the rest of the course, because of the way we're going to show it on the diagram is the same in both ways. And then anything else, you know, if you have two classes that need to, this class needs, you know, class A needs some information from class B in order to get its job done, but it's not a has a relationship and it's not a is a relationship. We're just going to call that an association. Specifically, and I'm not thrilled with these examples. I didn't have time to change. These are, I'm going to, normally I praise Dr. Ochoa for his notes. I'm going to complain about him here. I'm not thrilled with these because the specific form of the attributes that he's showing here are not in a format that we're ultimately going to use. So that top one, which is abstracted, class name, attribute 1, attribute 2, all the way down to attribute n, method 1, method 2, all the way down to method n. That is, that's how this is going to work. Remember, at their core, what's the definition of a class? What is a class composed of? At the core, there's two parts, right? What's the two parts that make up a class?
Is name one of them?
Name, okay. Now what are the two parts that make up that named class?
Oh, attributes and methods.
Attributes and methods, right? That's all they are. Remember, a class, if you think of it as an object, attributes describe the state of the object at any point in time, and methods are there to modify the attributes. We go back to early object definition. Anything that you are looking at in your environment right now that's an object, you can describe its state, that would be its attributes, and you can change its state, that's its methods. Now, of the methods, you know, let's say you have 12 attributes. As you know, you have a setter and getter, and generally you're going to have a setter and a getter for every attribute. And so that would be 12 attributes, that's 24 setters and getters. Don't include those in your class model. That's information that's assumed to be there that adds a lot of clutter, but doesn't add value to your class model. So I'm saying don't. Now that's a style choice, right? That's specific, you know, it's technically incorrect, but I'm saying don't add those in. As a reminder, make all your attributes private. Make most of your methods then become public. Those are the ones where you're saying this, you know, you ask, what do I need this object to do? What are other entities going to ask this object to do? You make those methods public, and you make all your setters and getters public. That way, the attributes are private. Remember, the primary benefit of object-oriented programming is this data encapsulation. Nobody can screw around with my data unless I let them. So attributes are private. And yet, people need to know the state of the object, right? Other classes will need to know the state of the object. if I'm going to do a ship simulation, it might be good if the ships know where the other ships are. Oh, okay. So, or it might be good if the port manager knows where all the ships are. So it needs to be able to query the ship. Where are you? What's your exit location? What's your heading? What's your speed? Those are the getters. And if it's a, you think of in terms of a FAA and a air traffic controller, they should be able to also modify the flight path of the plane, assuming a compliant pilot, where you're saying, okay, I need you to change your heading. So those would be the setters. All right, so the idea behind the class, you're protecting your data, but you do have to have some kind of a public access. Otherwise, it's the class is useless. If the class has private data and all the methods are private, nobody can interact with that class. There's no value to having it. So 2 things: attributes describe the state of the object, and then methods tend to modify or report on the state of the object. Now, if we go down here to this bank account class, and it's called bank account. And then the only thing I'm going to add here is the attributes are private. Owner. Okay, let's say the owner, I don't know, it's a string. Owner name, it's going to be string. And it's private. Make all your attributes private. So the format is $, private. Name of this thing is : data type. And then balance, $, because it's a private balance. And then this is going to be double. So it's always a visibility modifier, the name of the thing, : the data type. And then that's it. You don't put any explanations in of what it's doing or anything like that in the diagram itself. But that's why I'm going to ask you, for every class that you have, you should have a paragraph describing what the class does. What is its job? Why is it there? What do these methods do? And then in the diagram itself, it's just shorthand. For the methods, it's a similar thing, but methods tend to be public. Public, you preface with a plus sign. Deposit. Deposit probably doesn't do anything in terms of returning a value, so it's going to have a return type of void. So for methods, it's visibility modifier, which is usually a plus sign, the name of the method, and then : return type. And I'm going to be uncaring if we do. You can withdraw money. Now notice that the return type is void. Deposit is void, withdrawal is void. But what did they do? What they're going to do is a deposit is actually going to modify the value of the balance, and withdrawal is going to modify the value of the balance. So remember, attributes describe the state of the object at any point in time. Methods modify or report on the state. So for instance, we could do, whoops. And that would actually return the balance that's in the account, right? If you said, oh, I want to know how much money is in my account, that's actually returning a value. Now, by the way, deposit, which is listed here as a blank, actually you need to say how much money you're putting in. And I'm going to be pretty loose about this. So I don't care if you leave that blank or if you include the parameter list in there, which is preferable, or if you do another, there's actually another form where you would put the parameter list out to the right of the colon. I'm going to be really loose about that. I'm not going to worry about that. If you find a style choice that you like, just be consistent. Okay, so that's how to make an individual class. Is it all coming back to you? The night sweats? Okay. Now, what if we want to show I'm going to assume we know what inheritance is. The notation for inheritance is an arrow, and the arrow points from the child to the parent. And again, I generally talk about parent-child. The correct term is superclass, subclass, but most people say parent-child. You can say either one. If you have multiple children, which is normal in an inheritance relationship, because why do you have an inheritance? You have a generic upper level object, and then you have specific versions with different behavior for the extended or the child objects. Well, if you only need to have one extension, you probably just could have put it up in the parent class anyway. The reason you have extensions is because you have two or more similar classes with different behavior. And so you have the generic class up top extended to two or more different types. Again, generic ship extends to cruise ship, container vessel, tanker, tugboat, whatever. Okay, it's an arrow. And this is a silly way to miss points on a deliverable, is just to have the wrong connector connecting the two classes in your UML diagram. If it's inheritance, it's an arrow. For association, I'm going to skip a couple because he starts with association and then he goes specifically to the aggregation composition. We're going to go to the diamonds. So you have here, we're using, this is slightly different from 225, blank diamonds for aggregation, where you're describing at each end how many you may have, and filled in diamonds for composition. So you're showing the two relationships. I'm not going to, like I said before, I'm not going to worry too much about the distinction between aggregation and composition, but I am going to worry about diamonds versus arrows, because they really do mean different things in the context of the UML diagram. Okay, so questions about what I expect for the UML diagram in a deliverable. Okay, my expectation is this. You're going to have a section that says, you know, design or whatever I called it in your template. And you're going to have a short introductory paragraph talking about, hey, this section tells you all about the design. And then you're going to have a little subheading for each class. Here's what the class does. Here's the individual class diagram. Here's what the next class does. Here's the individual class diagram. And then you're going to pull it all together with a UML diagram that shows the relationships between the two. Okay.
Is that going to be in the template?
That's in
like the order of all that?
Pardon?
Like the order of all that?
Yeah, so I gave you, I think, a simplistic software design document template, and I just expect somewhere, and I don't care how you order them, they could be alphabetically, they could be by order of what you think makes most sense to explain to someone reading this first, right? That's your choice. That's an editorial choice.
Okay. Professor, you're on mute.
Hey, I know, I'm talking to someone offline here. Okay. Someone being my wife. Okay. So what if it's not a is and not a has? I'm okay with you just doing this. Now notice he uses an arrow here. I don't like that arrow. I'm just saying give a line without any kind of a direction for any other relationship you think you need to show up. And And dun, 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 dun. Here we have the sheep-sheepdog game. I've got terrain, I've got sheep, I've got a dog. And then I ask, okay, how am I going to make a model? Well, what do I need? You're right. You go through and you say, what do you need? And you start to say, oh, I need a class for the dog. I need a class for the sheep. I need a class for the terrain. And then you're asking yourself, okay, what do I need to describe the dog? What do I need to describe the sheep, right? Those are the attributes. What do I need to describe the terrain? Those are the attributes. And then asking, oh, okay, what behaviors should the dog have? What might people ask the dog to do? What might these other classes need to know about the dog? And you do the same for the sheep and the same for the terrain. And you keep iterating that. You know, you shouldn't expect to nail it down the first time, but there is a little bit of time spent trying to take care of that. Are UML diagrams only for UAP used by pursuit? I've only heard them in the context of UML diagrams, but my experience is limited in the real world with these things. So I've only seen them in the context of the UML diagrams. There are, it won't shock you that prior to UML diagrams, people had all kinds of other diagrams too. So some of those may survive for the other programming paradigms. Again, people have been trying to come up with the magic formula for how the heck you understand software for 50 years. And we still are not there. Okay, so my class diagram might look like this, and there's some editorial choices here that I actually want to change. Oh, okay, I just decided the sheep and the dog, they're very similar. I'm gonna have a generic animal, and then I'll extend that to the sheep and I'll extend it to the dog. And I'm gonna get rid of, can I do this or is it a picture? It's a picture. I'm gonna extend that so I get the sheep and I get the dog. And then I have a, you know, not part of what's shown visually on the screen is, gosh, if this is a game, I need something to control the game. So I'm going to have a game controller, and the game controller needs to have sheep and dog and terrain. And in this case, the solid and the unfilled diamonds were one of or multiples. So that was the CS225 way. I'm not going to be really strict about that here. So I say, okay, the game controller has terrain, the game controller has sheep, the game controller has dog. And then you start making some, asking yourself questions. And I've come up with a solution here, which may or may not be a good solution. Here's the question. How does the sheep know where the dog is? See, that's the kind of question you don't think about until you're coding, right? We want to learn to think of these questions before coding. The sheep is always supposed to run away from the dog. That means the sheep needs to know where the dog is. So how does the sheep know where the dog is?
Is it that sheepdog attribute that has?
Right, so that's a solution. One solution is to say, oh, the sheep can have the dog as the attribute. And then when the dog gets created, remember the dog will only be created once. This is you got to be careful with this. The dog can only be created once. The game controller will actually build the dog object. Dog equals new dog. But then, remember how objects work, the name of the name dog there, which is a data type dog, the name dog is really a handle to a memory space. So what I could do is if I let dog also be a attribute of sheep, the game controller can say to the sheep, oh, here's the handle to the dog. And now the sheep internally, because the dog has an attribute, can always check where the dog is. And even though the dog is moving itself around, the sheep aren't going to move the dog. the dog is moving itself around, the sheep can always check internally and say, where's the dog, using the getters from the dog class. That's a solution. Another solution is not to have the dog as an attribute of the sheep class, not to have terrain as an attribute of the sheep class, and put all that responsibility up in the game controller. And say, okay, the game controller is going to be able to, is going to have to tell the sheep where the dog is so they can run away from it. Do those two solutions conceptually make sense? Okay, so that's the question. Which is better? I'm going to reframe it. They both have issues. Number one, whereas we're going to talk about in a few minutes, you don't want to put too much of the work in the game controller because you don't want one class that's doing all the work. Otherwise, why are you using object-oriented paradigm? So having it where the game controller tells the sheep where the dog is might be putting too much work in the game controller class. And think about it, that we have a move method down here in the generic animal class. We have a move method, and the move method takes no input parameters. But if I'm going to have a method where the game controller says, okay, sheep move, now here's the dog location, XY location, I have to create a new move method in the sheep class that has different parameters. Now the two subclasses, sheep and dog, are physically different, which is not great because, we want them to be anywhere where we can use a generic animal, we could use a sheep or a dog. So we'd like them to be as identical as possible. But if if the game controller is telling the sheep where the dog is, that means the sheep has to have an additional method that the dog doesn't necessarily have. And the reason the dog doesn't need to know where the sheep are is because the dog is controlled by the human player and the human's watching the screen. So the human knows where the sheep are. So there's an asymmetry there. So let's go with the other one. Let's say that we allow the sheep access to the memory space where the dog is by having, we create a dog attribute in the sheep, and then we push the game controller, when it creates the dog, it tells the sheep, okay, I'm going to set your dog attribute to this. So now the sheep always has visibility into where the dog is. That's also a change in the attributes between the sheep and the dog class. So again, they're not physically the same class. So you're having differences in your subclasses, which in theory could run into problems in the future because they're both of the generic animal class. And you want to always try to make your methods work for the generic animal class, and then it will always work for the sheep and always work for the dog. But here we've got some no matter which solution we do, we have some things that are unique to the sheep. So one is helpful because it pushes the work down into the sheep class, which is what you want to do. You want to push the work down to the class that's responsible for getting the work done, and the sheep should run away by themselves, right? We shouldn't have a puppet master telling the sheep which direction to run. The other one is putting too much work in the game controller, but both of them have the problem where we're introducing differences in the structure of the different classes, which could over time start to cause trouble. So no great solution. The solution is probably to have a completely different classes that do separate jobs that are beyond the scope of this course. But notice the sheep-sheepdog game is about as simple as it gets, guys, right? So, and already we have, we can manufacture controversy. Now I'm not thrilled with this diagram because I put the black arrows from the terrain to the sheep and the black diamond from the terrain to the sheep and to the dog to the sheep. And I did that because this was originally a CS225 diagram, I would say it would be better just to have the line without any connectors between terrain and sheep and dog and sheep, because even though the sheep has a dog attribute, it never actually creates a dog object. That happens in the game controller. But the sheep needs to know where the dog is, so there's a relationship between those two classes. Anytime a class, if it's not a is a and not a has a, but one class needs some information from another one in order to get the job done, we can connect those with a line. Okay, questions about that before we go on to the second topic? These are the kinds of things, whoops, that you never think about it until you're sitting there at 2 a.m. coding. Oh, I didn't think about that, right? How do you get good at thinking about these? Code stuff up, run into the problems, and then the next time you code stuff up, you'll remember that. Okay, second part, code complexity. I'm gonna give less. Gosh darn, where's it start? There we go. Low level design. The low level design is what we've just been talking about, actually, the class design. How do you physically construct the classes? And the process basically is you have an overall high level design, your architecture. You've decided what kind of programming you want to do, which in this class you're probably not going to be encountering that problem. But then you start to think about, okay, what classes do I need? Where do they go? How do they communicate with each other? What should they contain? What attributes should they have? What actions or methods, right? What actions can they take? So what methods should they have? These are questions that you should spend a fair amount of time on before you actually start coding. And there's a contradiction here with the agile process. We'll talk about in a little bit. But you should spend a fair amount of time on this stuff before you start coding, have some idea of your design. High level architecture, high level design is what we call architecture. Low level is the detailed, which focuses on the stuff we're going to talk about here. And what's the main thing you're really worried about? What's the main thing you're worried about when you design your software? What's the number one thing on your mind?
Make sure it works.
Make sure it works. And I'm going to say that's the second or maybe third thing that should be on your mind. The main thing is it maintainable? Is it easy to understand? If I needed to change something in the future, and you know you will, if I needed to change something in the future, have I made that for my future self a miserable experience or an easy experience? So the main thing you want to think about is making it maintainable, changeable, adaptable. The reason you push that as your main concern is if it doesn't work, who cares, right? So making it work is a given. That's just assumed to be everybody's goal. So the thing you want to do is, of course, you want to make it work. You want to make it work, but designed in such a way that if you need to modify something, you can. Now, think in terms of object-oriented design. What were the benefits of the object-oriented paradigm again?
It's a maintainability.
Maintainability, but why? How does it achieve it? And there's three specific things that we're hoping to get out of object-oriented design, but the fact that you have objects speaks to all three of them, and maintainability is one of them. Why would objects be more maintainable than non-objects in theory? I mean, we can always make bad design, right? In theory, why are objects helping you? Are they giving you a tool to make things more maintainable? let me put it this way. What was I said in CS225, well, this is the number one thing that you get out of object-oriented. And if someone, if I call you at 3 a.m. out of a deep sleep, what's the number one thing you get out of object-oriented? This is what you should say. Or if someone walks up onto the street, what do you get out of object-oriented? What's the main benefit? This is what you should say. What is that? You're either furiously looking at your 225 notes or no excuse. This is the thing. 20 years from now, if somebody asks you, encapsulation, particularly data encapsulation, right? Data encapsulation. But we can extend that idea to behavioral encapsulation so that these objects have boundaries where they interface with other objects. And you can change whatever you want inside an object as long as you don't change the boundary. And that is a huge benefit. You can upgrade your software, and when you do your upgrade, you just say, here's the boundary. You carve out a piece of your software, which might be one class or it might be 2 or 3 classes, but you fix a boundary and you say, we're going to do things different over here. But if we never change the boundary, then nobody else will ever know and nobody else will ever care. And so we can maintain and upgrade our software without messing up the whole system. Spaghetti spaghetti code is where everything is intertwined, like spaghetti. If you ever tried to pull out just one strand of spaghetti, a whole bunch of other strands move and come along with it. Meaning in code, if you have to change one piece here, it gets changed over there, which now all of a sudden it gets changed over there, right? So you have to keep doing a lot of these things. But if you have really clean design, and I'm not saying it's easy, you have really clean design, the idea is you're encapsulating, right? Data encapsulation and behavioral encapsulation in such a way that you can modify things. Let me ask you this. If I built a class whose job was to sort numbers, and you used the class and you put in a bunch of random numbers and they came back sorted, and that happened every time, would you care if I used bubble sort versus quick sort versus merge sort versus heap sort? Would you care how I did it, as long as I gave you back the correct result? No, but you shouldn't. So I can modify what I did inside my class, where I change how I sort things, and it doesn't affect you. That's the encapsulation idea. So what you want to do is build classes that, of course, have to communicate with other classes, because otherwise there's no value to the object-oriented design. But they don't communicate with other classes so much that you've effectively got spaghetti code. And this is about, it's really, again, we're assuming that no matter how you create it, it's correct, right? It gives the correct result. But now, since that's a given, we're going to say, okay, so the next layer that we're concerned about, which is really becomes the primary concern because everybody assumes correctness is in there, is going to be, how do we make good classes? And there's basically 2 things that you want to deal with. This is all motivation stuff here. That's what these slides are, motivation. So minimizing, I'm going to get to the punchlines here. We talked about abstraction for models, but it's the same thing with abstraction with classes. You think you think of your classes as a top level entity, right? You think in one-liners for them a lot of times. Oh, what's that? That's the sheep. What's that? That's the sheepdog. What's that? That's the game. Oh, wait, but isn't the game made up of terrain, sheep, sheepdog, and a game controller? Oh, yeah, but it's the game. And you know this. You're playing online games, a lot of you, that have probably hundreds of thousands or millions of lines of code, and you don't worry about that detail. You just say, that's a game I like. What does it do? Oh, you move around and shoot stuff. Oh, right? Abstraction. Encapsulation. Information hiding is a similar form for this stuff. And we can get down into these, into the details in these, but what I really want you to focus on are the last two: low coupling, high cohesion. And so I'm going to skip through these slides and give you the punchlines here. Coupling. Coupling. How much does a class depend on other class to get its job done? For example, in my sheepdog game, the sheep are really dependent on other classes. It needs the dog class to know where the dog is. It needs the terrain class to know where it can run to. That might be a sign that I've got bad design. And if you've got a class that's pinging all over the place, in order to get my job done, I need to know about all these other classes, or I need other classes to do part of my job for me, that may be bad design. That's called coupling. How much are these two classes coupled together? If you have two classes and they're constantly, and it's not just through iteration that they're constantly pinging each other. I mean, every method in this class needs to have an attribute from this class in order to make it work. Well, that's probably bad design. You need to think about, well, gosh, maybe I should take these attributes over here and move them to the class that actually uses them more. Or maybe both of these class designs are bad and I should scrap it and come up with a different class.
So like, what if you have kind of a client server-esque kind of thing? Like for our project, you know, we have our Canvas interface and our Outlook interface. We were thinking each of those would be a class, and then like a go-between class in between that would like take stuff from the Canvas and put it out to the Outlook. Is that bad?
Yeah, so yeah, so that's tough. And what you can do is you can lay out, you can physically lay out and do analysis as to how much that intermediate class needs to work with both of these other ones. And then, okay, if it looks like the, you know, either of those classes can't do their job without the other one. Now the thing about that one where you're transferring, you're saying you have a class that just transfers data between the two?
Yeah, but it also might do more depending on how complex.
Well, I would
you know,
recommend
like
that I would recommend that it do the bare bones, right? And if it needs to do more, that may be a completely different class.
That's fair.
A class whose job is just to transfer data between the two and translate between the two, that's probably legitimate.
Cool.
Because that's its job, right? Some of these you can't get away from too much. But for your Outlook class, let's say you have a class who's grabbing data from Outlook. It shouldn't have to talk to other classes, at least for that phase, right? It shouldn't have to pull another class in and ask that other class to run some kind of a method in order to just pull the data from Outlook.
Right.
I'm talking, you know, we're starting with simple design. People can come up with really non-intuitive, but really elegant designs. And I'm not one of those people that that are like, oh no, I'll have a class just to do this job. You know, that's a good thing, by the way, a class just to do this job. And you know, you at least consider it. And maybe it works out where like, oh yeah. And if you do that, the class that used to have to every now and then talk to other classes doesn't have to anymore, because this one does it only when it's doing its job, like the transfer. And that actually makes sense in the context of that job. But if you had something that was doing transfer plus a whole bunch of other stuff, I would say at least look at it and make a conscious decision about that, because it may be that class, all that other stuff, if all that other stuff doesn't need to be talking to those other classes, maybe you should separate the functionality of that class into two classes, one that does just the transfer and it makes sense to talk back and forth, and one that does what you're calling the other stuff and it doesn't have to get involved with those other classes. So that's coupling.
Yeah, that makes sense. Thanks.
Okay, now coupling, of course, classes have to talk to each other to some degree. You want it to be a minimum to get all the work done. Remember, classes literally send messages to each other in the Java virtual machine. And then cohesion is how much does a class use its internal resources. So for example, if you've got 10 attributes, but your class never uses 2 of them, maybe those attributes shouldn't be there. Or if you've got 5 methods, but the only class that ever uses one of those methods is in another class, right? So your class internally doesn't use it, only uses 4 of the 5. Maybe that method should be pushed out to the other class. So it's, one is, you know, what the goal here is, you want these things to be as independent as it makes sense for the job of the program to get the job done, as independent as they can. That's to reduce the coupling, so that if you change something here, it's not likely to affect something 3 classes away. And then you want high cohesion, meaning the stuff you have in a class is actually needed for the class. It actually uses it. It uses the attributes, it uses the methods. Oh, and the methods don't have a lot of, necessarily have a lot of local scoped variables. You actually use the attributes. All the methods use at least 2 of the attributes or something like that. And there are mechanisms by which you do analysis and measure the degree of coupling and measure the degree of cohesion for your overall program and come up with metrics for that stuff, which, by the way, are not in the notes, but you can find these things. The idea behind reducing, the idea is you have low coupling and high cohesion, meaning if you have to change something within a class, it's less likely to affect the other classes. But if you have high coupling and low cohesion, then they tend to go together, right? Because if my class doesn't use the stuff I need, the stuff I need must be somewhere else. So that means your cohesion is low and your coupling is high. And then you change that class, you very likely may have to change other classes. So you can see this from a maintainability standpoint. That's a problem. Now, we don't worry too much about maintainability in this class because this class doesn't last 5 years. It seems like it, but it doesn't last 5 years or 10 years. But think of it even from a program, agile development. And there's a bit of a contradiction coming. From an agile development standpoint, you're building out your code a bit at a time. And what you would like to know is if you finish one class and then you build out another class, you would like to not have to change the class that was already finished, which means that you need to have good design up front. But what's the contradiction? The contradiction in Agile is you never do everything up front. That's the old waterfall method, right? The complete design, the complete requirement set, the complete test set before you start programming. And here what you're going to have is a good idea of the design followed by development and development and development, where we would expect the design to change as a result of the implementation of the code. So there is a contradiction here. And if you get into really extreme agile methods, they have the foggiest notion of a design and they start doing like extreme programming where they're designing, or test-based programming where they're coding, and they build the design up as they go. Well, what's the risk there? The risk is you may have made some early decisions about your design or your architecture that really turn out to be horrible by the time you're done. So what I'm trying to do here, we have a balance in this class where I'm asking you to put together a good design for your software design document, at least at the class level. And then as you implement, we would expect as you go through your sprints that you're going to have to make some modifications. But ideally, you've made a good enough guess up front that the modifications aren't going to be horrible, horrible. Does that make sense? And here's a nice picture that shows this. You want this, see the one on the bad one on the left? In order for any of those classes to do anything, they have to get a whole bunch of other classes involved. That's what all those arrows of data transfer are. And that's not what you want. And they're not doing much internally, right? They're doing things across classes, as opposed to the one on the right, high cohesion and low coupling. They're doing all their work inside the class, and then they're reporting out or getting, getting some requests for updates from the other classes, but the bulk of the work is being done inside the class. Okay. So that's what you, and this goes into details of what I just said. This is the details of coupling. You will, of course, they have to talk some. Otherwise, we wouldn't have an object-oriented paradigm. But what you don't want is just this constant, every time one class needs to do something, it has to chatter with another class. Now, generally, a class isn't going to do anything, at least in our kinds of projects, unless somebody asks it to. So there's one request. And sometimes it reports back. So that's one. But while it's doing the job, it shouldn't be having to chatter with a bunch of other classes. And then this is repeating in more detail. Same thing with cohesion. You want to be able to use the stuff, right? Do the job internal to your class. If it's the job of that class to do a job, it should be able to do the job. Not easy, by the way. This is not trivial stuff. And it gets weird, right? Well, what if I have a class that's composed of other classes, like I have a flight of aircraft and it's composed of several aircraft. Well, wait a minute, aren't I breaking the rule because my flight class is going to communicate with the aircraft class? Yeah, but if the aircraft are attributes of the flight class, that's internal to the flight class. Does that make sense? Okay. Now we're finally here, and I'm going to go through these relatively quickly. Good to know kind of things, but not. We're not going to encounter it in the course. You know, when you move on to more sophisticated software engineering courses, this will be revisited. So the architecture, the high-level stuff, right? High-level architecture. Basically, this presents different forms of architecture, and again, this gets into the contradiction that I talked about earlier with Agile. You know, people kind of blend this sometimes where they say, okay, before we start doing our Agile development, we actually are going to nail down the architecture, the high level format of this. And that's probably a good idea. In this class, I'm asking you to get a pretty good idea of your class design, which is actually low level, but that's because we tend not to have a high level projects that are complex enough to really have to worry about the high level architecture. But as you would expect, there's different forms of architectures, okay? Non-functional stuff, reliability. Okay, so here's just different architectures that you may encounter. One is the layered architecture. This is very common. Presentation level, business layer, services layer, persistence layer, database layer. Oh, what would those be? So here's how this may work. Like the presentation layer, that's the thing that you actually see on the screen. So, you know, think about it from a banking application. Okay, on my screen, what do I see? Oh, my bank login page. All right, so I put in my username and my password, and that request is going to go through several layers. The business layer, where it's saying, okay, what's the business at hand? And technically, this would be more of a truly in the business, corporate business context. But what are these jobs that need to get done? What are the units? So, okay, so at the business layer, I probably have a specific login server, which is separate from my account balance server, right? So I have a login server. And then the services layer, okay, that's going to go down and say, I need you to get this job done for me. Someone is trying to log in. That's a service that layer provides. Okay, we can provide the login, the verification of the username, password. And then you go down to persistence layer and database. And I'm going to just worry about database right now. It checks against, oh yeah, username, password. That sounds good. Okay, let the guy in. And then those requests go back up and the presentation layer changes now to my account balance, let's say. But you can see where you're separating the concerns. Every layer has a specific job. And if I change one layer, but I don't change the boundary, I can maintain this large system. So maybe you do a database upgrade, but as long as you didn't change the boundary between the database layer and the persistence layer, you don't really care. Now this persistence layer, by the way, I'm interpreting that as, what does that even mean? What that means is you have to have the database always in a state that is logical. And if you take a database class, they'll talk about this, especially if you take a asynchronous transaction management database class. You always have to have the database in a state that makes perfect sense. And you may notice if you're in Campus Solutions, if you open up one page on Campus Solutions and then you try to open up another tab and open the same page, it doesn't like that. And the reason is you might make partial changes on the separate pages and it confuses out Campus Solutions as to what the state of the database is. So you always have to have this persistence layer where if somebody makes a change, then that change persists. And if they don't make a change, you can roll back to the previous state and that state persists. You'll see this with your bank account all the time. If you're at the ATM and you take money out, then your bank account balance has to drop. But it's more important if you put money in, your bank account goes up. That better persist, right? Hey, I just added 200 bucks to my account. And it said it went up, but the next day it didn't record it. Well, that's bad, right? You want persistence there. All right. So anyway, these different layers, that's one form of architecture. Event driven. This one happens a lot in the game. This is in the gaming community. It's all about event driven stuff, right? Because that's how the game is played. And how can you, what can you complain about with an online game? Oh, lag. I pushed the button, nothing happened, and something bad happened to my character. This is all about event stuff. So it's all about a request is made of the system, and then you ship that event out based on the type of event to separate units, right? You don't have one big thing because it wouldn't react fast enough. You have separate event handlers, servers for different kinds of events to offload that traffic. I'll let you read through those. Microkernel. Here's where you have, and you see this with APIs, right? Your browser is an example of this. There's a core system, and then you can add on to it through plugins, through APIs. And there's a lot of these around. Right? You have a lot of software that you can download, and it says, okay, here's our API. What's the A? Abstract Programming Interface, where they provide you basically with the interface. And that's always the trick with this stuff. Worry about interfaces. As long as the interface doesn't change, you can do whatever you want. Okay, but they're saying, look, if you want to use our software, you have to fulfill the obligations of this interface. Now, this is a good one for, thank you. Yeah, because the application is interfacing with the program. This is not a bad one, I think, for projects, because again, if you think about, okay, we might want to expand this in the future. Oh, but we don't know what these expansions are. If you think along these lines, basically, if you build a core system and then you have the core system as functionality that it presents outward to the external world, someone else can build the plugin component as long as you're telling them how to interface with this thing. I'm trying to think. This actually worked with a while ago. We were under a couple of years ago. We were under FAA contract, and the FAA was going to give us a simulator, and then we were going to use the simulator. And the FAA was late. They kept delaying. And so our people, John Pesci specifically, and Jake Neighbors, said, well, we're going to build a pretend simulator while we're going to build a simulator of the simulator while we're waiting for the FAA one. Well, they ended up doing such a good job that FAA bought their simulator. And then they handed it to 4 other universities, and it basically became a plugin. That simulator had an interface, and then the other universities were developing AI as to what should happen inside the simulator. Well, these were plugins, right? You could plug in your own brain, basically, to the simulator to control the behavior of the entities inside the simulator. That would be a plug-in kind of approach. Space-based. I'm not so familiar with this one, but these are going to be, think about, cloud services, right? Everything is built around moving things out in a physically distributed way, and then you've got this virtual part that is connecting these things. These are going to be the parallel systems, the distributed systems, the cloud-based systems, these kinds of things. Okay. So that's all we need to talk about with those, other than you have always in engineering, I don't care what engineering discipline you're in, these conflicting goals, right? All the aeronautical engineers want to make an infinitely strong airplane that doesn't weigh anything. So you always have these conflicting goals. And you have the conflicting goals here. Well, wait a minute, ease of maintenance. Well, that's the separation stuff. Performance. Well, wait a minute, if you have to go through a bunch of different layers, for example, in that layered architecture, is that going to affect the performance? What if it's a gaming system and you have these layers? Well, by the time the person puts in their request for what their character should do on the screen, and it travels through the internet and it hits those layers and goes down, 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 back up, 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 and back through the internet, might be too much lag. Maybe that's a bad architecture for the game. So you want performance, but you still want separation of jobs so that you can maintain the thing. You want to have the ability to test your system. Well, can you test a partial system? That may be tough. Okay. All right, so I want you to be aware of these things. We're not going to, I don't think that the architecture portion is going to show up much in the course as in your project work. The detailed design stuff is going to be far more important. Okay. Do we have questions? That's the material that I wanted to cover today. Do we have questions? Okay. I'm all set then, and we'll have office hours on Wednesday as usual. And I will see you then. Thank you for being here.
Thanks.
All right, thanks guys. Have a good day.